Hello, everyone. Thank you for coming to this poster/presentation. My name is Salvador Sosa. I am a postdoc at the University of New Mexico, and I have the great pleasure of talking about our research on behalf of our collaboration, which is formed by Dr. Sandra Bidron from the University of New Mexico, Trudy Bolin from UNM, Dr. John Carey from TechX Corporation, Mark Cortin, Bill Hartman, Tim Presnell, and Dan Swanson from Ion Linac Systems in Albuquerque. The title of this talk is Electromagnetic Simulations of a Novel Proton Linac using VSim on HPC. So the particular Linac that I'm talking about is being designed by Ion Linac Systems, ILS, and this is intended to be for a medical application called boron neutron capture therapy, which requires a beam of epithermal neutrons, which are in turn produced by a high intensity, low energy proton beam, which is produced by this Linac. So because of the proprietary design, the structure maximizes the energy gain, keeping the high transmission of the beam, while keeping a very compact footprint, which makes it robust, affordable for applications like this, where you have to place this machine inside a small facility like a hospital, and you want to make it cheaper. And part of the UNM collaboration with ILS is to develop artificial intelligence enabled controllers, which may in turn help reduce the cost of operation of a machine like this. So for any AI model that you plan to train, you need to have a lot of data. And we're trying to use simulated data just because running the machine is expensive. So we have a very detailed simulation of the machine, which we run on VSim. VSim is an electromagnetic code that was developed by TechX, another of our collaborators. And VSim is one of the most cited plasma codes around. It has electrostatic and electromagnetic solvers that we need for beam dynamic simulations and RF simulations, so it's very suited for this. But in addition, yeah, you can include particles, collisions, reactions. It has a lot of features. One of them is that it scales really good into high performance computing. And by integrating VSim with HPC, we hope to enable several applications that are only allowed by having a large amount of simulations, which may be complex. And in order to make it practical, we need to have short or small computing times. So VSim uses an hexahedral mesh to resolve the material, the particles, and to locally solve the electrodynamic equations. And we are using VSim on THETA. THETA is a supercomputer hosted by the Argonne Leadership Computer Facility. It is a user facility that has around 280,000 computing cores. And you can see more details about it on this website. So currently we are using THETA for ENM simulations with VSim for optimization and several AI algorithms. So for this contribution, we're looking into a simple electromagnetic problem, which is to calculate the RFQ fundamental mode of operation, which is at 200 megahertz. So we use VSim on this simulation, but because we have a very large number of hexahedrons, around 37 million, in fact. So we want to really expedite this type of calculations as much as possible. So you can see here the longitudinal electric field corresponding to the fundamental mode of operation. And so we use THETA to calculate this electromagnetic problem. So the general parallelization concept is you divide the problem, whatever problem that may be, into smaller parts. You assign each of these smaller parts into an individual hardware unit and you run them at the same time. So you can see here the efficiency, the computation time as a function of the number of computing cores used for this, for a reduced version of this simulation. And you can see we get in this laptop where I'm doing this recording right now, the same simulation takes about 3 hours, while using the optimized hardware on THETA, the same simulation runs in 10 minutes. So this is going to become really useful and efficient when we start the data production part of and training of something like a surrogate model or any AI project. So finally, I want to acknowledge our funding sources, the Department of Energy through the Office of Science, Office of High Energy Physics under this award number, acknowledge the ALCF computing resources supported under this contract, as well as computing resources from Element Aero, one of our collaborators. Thank you. Please go check our paper for more details.